Morning. How are you guys? A lot. Got a lot to do before Thanksgiving.
Yeah. Well, it's more of like
Right. What's that?
I said for some reason I have to just not going to get
Thanks.
Well,
Good luck. All right. So today I wanted to essentially pick up where we left off and then finish covering the secondary treatment in terms of recycle systems for activated sludge. Last time we really covered what it would be like to have an aeration basin with no recycle. So if we just looked at a system that kind of looked like that, if we were to draw a mass balance around it, or a control volume. And what I want to do today is see if we can get through the mechanics of how we calculate essentially the transport of mass and the growth of bacteria through this system if you do have the recycle, and then see if we can get into some of the BOD material, because some of that's on your homework. I did post the homeworks, so that'll be your last homework, and that'll be due a Thursday before finals. Okay, so we talked a little bit about this already, but with a recycle system, our clarifier, we are assuming when it's working well, is removing all bacteria and effluent. So XE then should be 0. That means that we have all the sludge that's potentially going to leave the system is going to be really only leaving in the WAS line, the waste activated sludge. One thing we could also note here is the X, let's say clarifier, is going to be the same as this XR for here, and it's going to be the same as XW. I guess that probably put it as R right there. But essentially, all I'm saying here is just making the obvious point that we have flow going through a pipe. The pipe splits off in 2 directions. It's the same concentration in both, right? There's nothing that changed the concentration right here because we, took more or less one way or the other. It's the same stuff going either way. Okay, so just a kind of obvious point there, I guess I'll leave that as if this is XR and this is XW, those two are equal. Okay, so just to kind of have those written out a little more clearly here, one of the assumptions we're making is that there's no biological activity happening in the clarifier, and that's not true, but it's reasonable given that we're not activating it with plenty of oxygen, right? We are no longer bubbling stuff through it. We actually want things to settle, so we don't want a lot of bubbles in there. So it's true enough. Certainly there's going to be some activity, but it's not our primary source of biodegradation. I mentioned the XW, all of that. It's the same that applies for the substrate concentration. S is going to be, the S here. Well, actually, there's going to be a little more to it. So if we take a look at the substrate balance, the S in the tank is the same S that's going to be in the clarifier, which means that's the same S that's going to be here in the effluent, and the same S because this is just dissolved stuff, right? This is not separating by solids. We're not getting any change. The clarifier is not changing S. So, given that, the same S is here, and is here, and is here. So the balance on the substrate is basically the same throughout. We already talked about X through that system. Just kind of summarize it there for you. Okay, so that brings us to one of the most important concepts to regulating what happens in your activated sludge system, which is the food to mass ratio. And we talked about last time the fact that we had some yield coefficient. There's some amount of bacteria that we yield per mass of food that we consume, or the bacteria consume. And that relates directly to this food to mass ratio in that how much, the concept is how much food do the bacteria have compared to how much mass of bacteria do we have in the system. So we write that as F/M, and I put that in quotes here because we're not doing a division. This is not food divided by mass. That's what it means, but we don't ever break this apart. That's always one unit. Or, that's the symbol. We don't break that symbol apart. So just leave F/M as that, or you could write as food to mass ratio, I suppose. But essentially what we're taking there is the milligrams of BOD, the food, per liter, and divide that by the amount of mass per liter, so milligrams mass of bacteria, milligrams VSS per liter. The liters will cancel, and we also have days here. So this is not just food to mass, this is food per day per mass. Okay, so this is a rate of the amount of food the bacteria have in ratio to how much bacteria there are. So that's typically in days. So I'll say this is a daily food to mass ratio in some sense. Okay, so considering that, and considering the fact that we know that our growth rate constant, mu, depends on how much food we have, that kind of tells us why this is important. If we have a lot of food compared to the amount of mass we have, then they should be growing faster, right? So that's kind of the concept here. The mu is dependent on S, so the S is really important in relation to our X, the VSS. Okay. In terms of operation, we really want to have good control over the food to mass ratio because we want to be able to control how much S is being consumed. That's kind of our goal. But we also want to control what types of bacteria we have. If we starve certain types of bacteria, then other types might grow in abundance. Maybe that can be a problem. Let's say if we have a lot of fatty substances in our wastewater and we get a lot of fat-consuming bacteria instead of kind of a standard amount, maybe they'll be producing lots of lipids and bubbles essentially and cause a flotation problem, which then you can tell if your system is kind of relying on the fact that you're separating everything in the clarifier. If you get flotation, sludge flotation, because you have a different bacteria growing and producing weird stuff, then you have a lot of bacteria leaving. Then you don't have as much bacteria recycled back into your aeration basin, and you have a big problem. It's a compounding problem, and it's a problem that wastewater treatment plants do deal with sometimes, and it really creates a range of problems, including untreated waste leaving, lots of bacteria leaving, and bad smells because now you're no longer necessarily getting all that aerobic process done, which is kind of smells like earthy a little bit. I mean, it's maybe a little unpleasant, but not a lot unpleasant if you have a properly running aeration tank. Whereas if you have some anaerobic processes going, that's going to be very unpleasant. Okay. Yeah, those are kind of the points that I have up there. So in terms of the definition, this food to mass ratio, we can define it with a flow rate. So I mentioned, could take S divided by X and divide that by the time. But perhaps a simpler way to do that is, or a more convenient way would be to take the flow rate, which gives you the that per time, divide that by the volume. So flow rate divided by volume, that's per time, and take your substrate concentration divided by your x. Okay. So that kind of brings us to the concept of hydraulic versus solids retention time. So hydraulic retention time is a little straightforward. Some of the assumptions we made earlier are going to come to play here. We've talked about hydraulic retention time quite often. That's theta equals V over Q. So we've covered that thoroughly, but in this system, we have our control volume sketched around a 2-unit system. So this might get a little confusing here when you have to think about, okay, well, we have this aeration tank and we have this clarifier. What's going on? Well, the assumption that there's no biological activity going on in the clarifier is really what simplifies this process for us. Because if there's no biological activity there, then essentially it's not contributing to the reactor. The reactor is where S changes and X changes. So X and S are growing or depleting here, changing in some manner. Well, this is the only volume that matters. So even though we might have some amount of flow that's changed one direction or the other out of the clarifier, what really matters is the flow going out and in the aeration tank. And so if you're worried that the recycle rate's going to change the hydraulic retention time and be some sort of concern, well, that's one reason we draw this control volume way out here, is because now the Q here is going to be equal to QE plus QW. So the net Q doesn't really change based on how much you recycle. If you recycle less, then more is going out the effluent. If you recycle more, it's going to be a little less coming out the effluent. But the net balance is going to be the same. Whatever's coming in is going out. We're not accumulating water inside that control volume. Okay. So, given that, the V that we're going to use is simply the V right here, the volume of the aeration basin. So the hydraulic retention time seems like it could be complicated, but because of the assumptions we make, it's pretty straightforward. Okay. For the solids retention time, this is essentially the X, the mass of bacteria in our system. How long does that stay in our system? Turns out that's a pretty important parameter because we have to know or have some control over the age of the cells. It's going to control the mass of cells in there per volume concentration. And what we're going to talk about or refer to when we talk about solid retention time is theta C for cell. Some people call it SRT, so solid retention time. And this one is changed when we change the recycle rate. More accurately, I guess we'll say, is we can manipulate it by changing the amount of waste that we're, the QW, the flow rate of the waste line. Because in that case, we do not have any X going out here, XE equals 0, so the XR here, which is equal to XW, really controls our system in terms of what's happening to X, right? If we have X growing, we have a little bit coming in, likely, not a lot. And so it's essentially what's growing and what's leaving there. If we allow less to leave, then we just are going to have a higher amount of it inside here. Okay, so theta C is not equal to the hydraulic retention time. So make sure that you kind of distinguish those two systems. Okay, if we consider how we would derive theta C, this is essentially the mass of bacteria And then we can divide the mass of bacteria by the flow rate. Let's see. So Qx is going to give us the mass, and then on the bottom we're going to have mass per time. We divide mass by mass per time, we'll get time, right? So that's kind of what we're looking for. So Vx here, this is in that volume, we have some amount of x. We're going to divide that by, our hydraulic retention time theta is V over Q. So we're setting up something similar here, V over Q, except we're dealing with the solids. So it's going to be Vx divided by the total Qs. So it'll be like the analogous equation is then Vx divided by Q total times x, or where the x is relevant. So that's where this equation is coming from. So we see Vx divided by the QE times XE and QW times XW. Well, we said QE is 0, so that means, and I forget, I can just do this. May not be in your way. So that means essentially our theta C is going to be Vx, it's going to simplify to Vx divided by QW XW. Okay, so that equation then is our solids retention time. It will describe the mass in the reactor divided by, or times the volume, divided by the flow rate times the mass that's leaving. Okay, so you'll have that equation as well. I wanted to go over kind of where that comes from, and kind of some of the context there. Okay, so given what we did last time and what we now have for this time, I'd like to take you through a problem. And we're not going to, it's a multi-step problem, so this is going to be a pretty good one to study from, to compare essentially a system that does not have recycle to a system that does have recycle. And what I'm going to do, since I'd like to progress a little quicker, is I'm going to give you the chance to take care of the non-recycle one on your own time. Remind you that essentially the example we worked last time is that type of a problem. And then focus most of our time today on the recycle. So I'm going to read through the problem. We've got some parameters up here, and then we'll kind of work through it a little bit. Okay, so this says, consider a wastewater treatment plant that's being renovated to include a return activated sludge, RAS line. Assume the influent MLVSS concentration is 0 without the recycled line. The following parameters are known about the reactor, which acts as a CSTR. Okay, the flow rate into the reactor is 0.01 cubic meters. Okay, so lots of parameters there. Part A says draw a schematic of an activated sludge system before and after the addition of the recycle line. So this is pretty straightforward. Before we add the recycle line, we probably have something that looks like this. Probably have a clarifier, and that's that. So kind of the pond example, maybe we don't even have the clarifier, but either way, that's kind of the setup. After would be having the clarifier and taking, of course, that recycle line and doing that. Okay, so that's just, making sure you're drawing a system. Part B says, what is the final substrate concentration in the no recycle system? So this goes back to what we did last time. So that's going to be a mass balance on X first to get you that one. Let you do that on your own time, but remember that we solved an equation. We derived a mass balance on X. The X ended up canceling out of the system, and we were left with a solution for S. Okay, part C says, what is the BOD5 removal efficiency for no recycle? Okay, and then what is the ml/VSS concentration for the no recycle. Again, that's essentially the problem we did last time, just a different setting, different parameters. So practice on your own. What I'll say is for this, the efficiency, of course, is going to be S naught minus S, so the amount we started with minus what we ended with, divided by what we started with. And for part B or D, we'll get a mass balance on substrate concentration will get us there. Okay, part E says if the sludge produced has a concentration of 12,500 milligrams VSS per liter, which is now recycled via the new recycle line at a flow of 150 cubic meters per day, what is the resulting, quote, influent ml/VSS concentration in milligrams per liter VSS entering the aeration tank? And I add a hint there to refer to your drawing. So make sure you sketch out the drawing again here. Have a nice clear depiction. And I'm going to jot down a couple of the equations that we just talked about recently. So that would be theta C Vx over Q, QW's XW. This one was, that was S naught. I'm just going to flip back real quick to make sure I get this right. Q S naught over Vx. Okay. All right, so take a few minutes, work on that, see if you can get the answer here to part E. I'll be back in just a moment. Okay, so hopefully you've had a chance to kind of take a look at this, think about how you'd approach it. So essentially, looking at the graph you might make here, you want to be solving for specifically the x that's in this line that's actually entering the system, not the x coming, into the wastewater treatment system here, but including the recycle, we need that x there. So it turns out it's actually kind of a simple problem. You didn't even really need the equations here. It was just going to be a mass balance essentially on this spot. Okay, so it's going to be, what's the x that's entering the system here based on the mass balance of the flow and the x values for each of these two influent streams. So essentially we've got, we could look at it like this, where we have a q x naught, and here we have a q r, and an xr, and then x is in question here, and I'm going to call it x naught prime, and that's going to be, we also have a q total, which is qr plus q. Okay, so this is the type of mass balance we've been solving for forever. There's no needed reactions or anything in this because there's, just two pipes mixing essentially. And so what we'll do is we'll say, well, first of all, kind of write out all these pieces, and then we can simply say that for our mass balance qx naught, which is equal to 0, and we can say that's going to be equal to essentially, well, you know what? Let me just rewrite this a little different. That it still is 0, but I'm just going to say that the qx naught plus qr xr is equal to, so that's the two things coming in is equal to what's going out, which is this x naught prime that we're solving for times that q total. Okay, so then if you solve that, you need to convert the flow rates properly. Then we should have a value of 1,850 milligrams VSS per liter. Okay. Does that make sense? Okay, so and there's a bit of a lesson here because I've given this on an exam before, and students immediately jumped to using these new equations and like trying to figure out how to manipulate them to get this mysterious x and not sure what they're actually solving for. But so really take your time to take a look at what the question's asking for. What does that mean in context of the drawing, the schematic? Make sure that as you're studying, you're considering that, how to interpret a problem is maybe even more important than knowing the equations of which equations, that will tell you which equations to use. So as you study, make sure you're understanding the values and the kind of the terminology as you go. Okay, so part F says, in the new system with the recycle line, the resulting food to mass ratio is 0.58 milligrams BOD5 per milligrams VSS per day. What is the new MLVSS concentration in milligrams per liter VSS? So go ahead and give this a minute. I'm going to go ahead and rewrite this equation here for you. So in this problem we have our food to mass ratio was given. So F to M is 0.58 milligrams BOD per milligrams VSS per day. Okay, and we're looking for the new MLVSS concentration, and really what that's referring to is the inside the aeration tank, what is the X? Okay, so that's the essentially what we're looking for is that new amount of X in the system, and that's after we started recycling the water. So we can say 0.58 is equal to, we will go ahead and use the F to M ratio here because we can solve for X in this manner. We can say that's going to be Q S naught divided by the X, and we can rearrange, solve for X. So X is going to be essentially Q S naught divided by V times that food to mass ratio. And here's again why I told you earlier not to separate the F and the M, because you might be tempted to say, oh, I need to multiply by the M and divide by the food, right? That's not going to work out so well for you. I guess maybe there's a chance you could do that if you worked this properly, but just keep it as F/M. Okay, so then we can say X is going to be equal to, we know our flow rate, 0.01 cubic meters per second. Probably going to need that in days, or to convert the food to mass ratio into days. Multiply this by our incoming substrate concentration. This was given here as 220 milligrams per liter. And we'll divide that by our volume, which is 550 cubic meters. And by the 0.58 milligrams BOD per milligrams VSS per day. Okay, we'll also need to do that conversion from seconds to days, and so I'll go ahead and do that on the top and say this, we'll multiply this by 86,400 seconds. No, did that wrong. 1 day per 86,400 seconds. Still doing that wrong. I'm sorry. We need days in the bottom. I was doing it right the first time. Okay. And that'll convert the seconds here into days. All right. So with that, when we solve, we should get a value X as 596 milligrams VSS per liter as our final answer. Okay, so that one was pretty straightforward. We had the food to mass ratio given, and essentially what we're saying is, given these conditions, if we know that the other values, if we knew the food to mass ratio, we know the substrate coming in, and we know the parameters of the system, it's going to be relatively obvious what the food to mass ratio is. There's not a lot of complexity right there. Okay. Then the last part of this problem is going to be, what is the flow rate of the waste sludge line? And we're going to go ahead and let's see how I solved this over here. Let's go ahead and use our 596 that we just solved. So let's not worry about this 400 here. So that's 596. from the previous problem. Okay, so give that a minute. See if you can find the flow rate of the sludge line given that. All right, so let's go back to this problem. Okay, so one more time, this is our system, just to make sure we know what we're looking at in terms of what the problem's asking for. QW here is kind of the question. And this really does control a lot of the system, as we'll see. So if we want to know what the QW is, well, our one equation that has that is theta C. We could also potentially look at the, if we had some way of finding Q in the effluent, which we don't, and we know what is coming in, we could solve it that way as well. Okay, so let's take our theta C equation. Given that we do know our solids retention time is 8 days, we can say, so theta C, we know that, and that's Vx divided by QW XW. So we can actually swap the theta C and the QW, get Vx divided by theta C XW. Okay. So based on the previous problem, we found the X value. So we know that QW then is going to be the Vx, which is 550 cubic meters, times is 596. Milligrams VSS per liter, divided by the 8 days, times XW. Okay, and the XW was actually given in a previous part of the problem. If we take a look here, the sludge concentration produced has a concentration of 12,500 milligrams per liter. So probably should have referenced this in the actual problem there for you, but this was kind of part of the system, was described as once it's now recycled, that's the amount produced in the recycle line. So we'll go ahead and use that here. And given that these are on different slides, it kind of makes sense if you didn't catch that. Certainly. Okay, so then we can solve QW then, based on all that, is going to be 2.98 cubic meters per day. All right. Does that make sense? All right, great. And one last little bit of the question is asked, what is the hydraulic retention time of the activated sludge before and after the recycle line has been added? So just take a quick moment to solve for that. Okay, so hopefully you had a chance, got to solve something for your hydraulic retention time at least before. If you convert it to days, that's 0.58 days. And then as we said earlier, there's no difference in the hydraulic retention time before and after recycle. So it's just 0.58 days for each. And that's, again, coming from the fact that we find a reason to draw this up every time, but we have our system. Even if we do have recycle, we assume that there's no biological activity. And so essentially, in terms of any purpose for the reactor, that volume is 0. So we can count the aeration, or excuse me, the clarifier as 0 volume because there's no reaction happening in it. Okay. Any questions or issues with all that? Okay, so what I want to do now is kind of speed through kind of the introductory portions of biological oxygen demand. Got some slides on that. We will finish the BOD slides when we come back, but I wanted to kind of get you the start and post the slides that I'm planning to go through, so you'll have something to go from if you are working on your homework and wanted to try to get it to completion before we finish the material. All right. And so I will post this. I have not yet posted this. I'm sorry I wasn't thinking that far ahead last night when I was preparing. But I'd like to go ahead and talk about oxygen demand generally. We talked about why we care about it. We covered kind of the intro to wastewater and the permitting and all that. So biochemical oxygen demand, BOD, you could call it biodegradable or biological oxygen demand. It's essentially the amount of oxygen that's going to be demanded. We can consider it as the microbe food, especially as a carbon source. And it's essentially going to be consumed, oxygen will be consumed in the presence of dissolved organics based on bacteria's action to do respiration, which is going to produce CO2, and to make new cells. So the process here, essentially BOD is a measurement of the amount of dissolved organics, but we are directly measuring the oxygen, right? So it's an estimate of the amount of dissolved organics based on the measurement of how much oxygen is being demanded by a biological system. Okay, that's different from what we would call the theoretical oxygen demand, which would be kind of the theoretical maximum amount of oxygen that a substance could demand in terms of doing an oxidation reaction. So if we had glucose, where we had like 1C6H12O6 plus some amount of oxygen going to oxidizing completely to CO2 and water. That's the theoretical, and we use that molar relationship, so we could solve this real quick. This would be 6 CO2s. Then we have, let's do the hydrogens. We have 12 hydrogens over here. We're going to need 6 water, so that's 12 hydrogens on either side. And then we need to balance oxygen, so we have 6 here, another 12, so that's 18. We had 6 over here, so we need 12 here, so 6 there. All right, so we would balance a chemical equation like that to solve and find, okay, theoretically, how many oxygen molecules are required to consume X number of glucose molecules. That's pure oxidation, as if you have a perfect combusting glucose into CO2 and water. That's not truly realistic in terms of especially in a biological sense. We're definitely not going to have that much conversion directly. And there's no way to know exactly how much or what specific type of organics we have in a normal water source. So if we were to take a sample from a lake, or from a wastewater treatment plant, there's no way we could know exactly the stoichiometry and all of that, right? So that's not realistic. It's just kind of a theoretical maximum. But if we did have something as simple as sugar in water, maybe then you could do it. But even then, it's still that theoretical, as if we had perfect oxidation of all of it. So a second method called chemical oxygen demand, it's not quite that theoretical. It's actually, rather than taking the theory and the writing it all out sort of method, here we just take a chemical reaction and essentially cause as much oxidation as we can with a really strong acid, really strong oxidizer, and sometimes ultraviolet light and high temperature to promote this combustion as thoroughly as we possibly can, and then observe how much essentially oxygen is consumed. There's a few ways to do that. Sometimes it's going to be a chemical that is, we can track its oxidation state to see how much of it has given an oxygen or whatever to do the oxidation. But essentially, it's a chemical measurement that takes an hour or two. You put it in an instrument and you let it burn, and it's going to measure that amount of oxygen consumption. So that's going to be a COD measurement. It's convenient because it's pretty quick, and it gives a kind of a practical quantification of how much oxygen the substances can demand. But that's also not truly realistic in terms of biological processes aren't going to go that far. That's going to be able to degrade some things that the biology simply cannot. So when we're using these three estimation tools for oxygen demand, we've got that theoretical. It's going to provide the greatest value, the largest value. The next largest is going to be the COD, and the final will be BOD. COD is often used to track things like landfill, leachate, pollution plumes, to see in your groundwater or something. You can get a pretty good estimation that whether or not you're contaminated by the landfill based on COD. It's used in some applications, some areas. In wastewater treatment, they're already doing so much biological stuff, and it's so biological related, they're typically just doing these BOD tests on a continual basis. The challenge and the kind of a problem with BOD is that it takes several days to actually get that biological activity, enough time to consume oxygen to really get a decent measurement. So that's why sometimes we prefer using COD. Okay, for the reactions, COD, of course, like we just saw with the glucose example, essentially we're going to be doing a combustion reaction, finding the combustion byproducts. For BOD, we're going to be taking organic matter. It's going to undergo respiration, digestion, and we're going to get some CO2, but we're also going to get new cells and some other stable byproducts like nitrate, nitrite, phosphate, some things like that that are not perfectly oxidized, right? These have oxygen groups in them. We took maybe an organic form of nitrogen or phosphorus, some DNA, some amino acids, whatever components, and converted it, but they're not necessarily all the way oxidized to the fullest extent that you might have. Okay, sorry. So, just a quick little recap on the nitrogen cycle here. The nitrogen can exert an oxygen demand as well. We kind of just noticed that a moment ago. I mentioned the nitrates, nitrites. But if you've got kind of a bioavailable form of nitrogen, like ammonia, find that in waste products with like urea, things like that. Essentially, that's the reduced form of nitrogen, and plants and biological entities can take that directly, but a lot of times, you can extract some energy from it as well, or you might be trying to treat it, and so you're going to have to add oxygen to convert it to nitrite, NO2 minus, and more oxygen to get it to nitrate, and then more to oxidize it further all the way to N2. Now, that might end up releasing oxygen, but that's kind of another story. So this process if we take a look at what's happening in the nitrogen cycle, the atmosphere has a surplus of N2. It is mostly N2 what we're breathing, and so there's plenty of nitrogen there. Certain organisms can fix that nitrogen into ammonia or into some organic nitrogen directly. Then something might be eating those plants or those organisms. That we get this organic matter. Then any decomposition or waste products, we typically get ammonia or ammonium. From there, nitrites, NO3, or NO2, and then from there, NO3. And of course, plants can assimilate this in different places, right? We apply nitrate as a fertilizer pretty often because it's relatively stable. If we apply ammonia, then we have some issues with it volatilizing or with kind of pH balance kind of things. We don't want to burn our crops. It'll be caustic in that manner. And then we have denitrifying bacteria that can release nitrogen gas back to the atmosphere. So in terms of wastewater treatment, a lot of times what we're aiming at is getting denitrification to happen. But we're going to have to convert the other portions first. In terms of oxygen demand, this is just kind of some context as to how nitrogen may add some oxygen demand to a system if that process needs to happen from here to here to here. That process will demand oxygen from the water as well. Okay, so how do we measure it? And why do we put this little 5 here? This is 5 days. This is a 5-day measurement. It's kind of the standard. We're just letting biological activity occur for 5 days in a bottle that's maybe room temperature or maybe a little bit warm. I think we usually incubate them, give them some comfortable conditions. We keep them in the dark, or at least have an amber vessel here, so that we have no algae growing, no photosynthesis occurring. So we don't want photosynthesis because that'll produce oxygen, skew our results, right? So we have to have an airtight bottle, make sure there's no oxygen exchange with the atmosphere, so that we can actually track how much oxygen is in our system. We need to protect it from light, and then we let the biological activity happen for 5 days. That may mean that we need to add some bacteria to it if we have a very dilute system. If we have a whole lot of waste that's really nasty junk and lots of stuff in it, it's going to demand a lot of oxygen. We're typically going to have to dilute because there's only a certain amount of oxygen that can dissolve in water. So we often have to dilute, and the way we calculate the BOD then is literally we measure the oxygen before and after our 5 days process. So we have an initial DOI, so dissolved oxygen initial, minus DO final, divided by a dilution factor. So it's pretty standard to use these 300 milliliter bottles. So this one would not be used. It's a culture bottle, about the same size, but we wouldn't use it because it's not dark, right? You'd have to put foil on it or something. But these bottles typically are about 300 milliliters, and so almost all what we do is we're going to be using a dilution factor that's some amount of wastewater in 300 milliliters total. So P is essentially that volume of wastewater divided by the volume total. So I'll say volume sample. You don't have to have a wastewater. It could be a river or a lake or something that you want to measure. So I'll say volume sample over the volume total is P, right? That's another way to phrase that. And so typically, that's going to be our volume of wastewater or whatever divided by 300 milliliters. That'll be in most problems. Of course, if the problem happened to say something else about the volume of the BOD chamber, adjust accordingly. All right, so that's pretty straightforward. The dilution factor there is just that ratio of sample to total. All right, I have a problem here, and I left the text, the writing from last time I solved it, because I wanted to go a little quicker today. This problem says we have a 10 milliliter sample mixed with enough water to fill a 300 milliliter bottle, has an initial DO of 9 milligrams per liter, and to help assure an accurate test, we want to have 2 milligrams per liter drop. So our little DO measuring devices, if we're close to the value where we started or close to 0, we're not so sure we can trust the instrument. So we want to have at least a little bit of a drop and at least a little bit of dissolved oxygen remaining to make sure we're not nearing the detection limits of that little instrument itself. Okay, that's kind of the context here. So we need at least a 2 milligram per liter drop and at least 2 milligrams per liter as the final value. So we have some confined range there where we have to be between those two spots. And so then the question's asking for what range of BOD would this dilution produce the desired results. So given that, we've got this little problem. It's solved here. And so just take a look at that, maybe work it on your own, and then take a look at the solutions. I'm going to pass through it. It is pretty straightforward. So I want to talk just a minute about adding a little more complexity to the system when we have to seed a dilution. So I mentioned earlier, a lot of times we're going to have to dilute heavily. We have a really high strength wastewater. So let me comment on this real quick. So a high strength wastewater is going to be something like 500 milligrams BOD per liter. So that, if you could fit 500 milligrams of oxygen in a liter of water, no problem, right? You could just directly measure it. But it turns out that our O2 saturation is something like 8 to 10 milligrams per liter of oxygen. Okay, so there's no way you can demand more than 8 milligrams per liter from that water. But our sample could theoretically demand 500, right? For a full strength, high strength wastewater, we could demand way more than is possible there. So we have to dilute it. When we dilute it, or perhaps if we're sampling maybe the disinfected effluent, we don't have enough bacteria to do anything with. So we have to add bacteria into the solution. Well, in order to keep the bacteria happy in our refrigerator so that we can add it when we want it, we have to have some biodegradable organics with the bacteria so that they stay happy. So when we do this, we add more BOD to our system because we have to. And so that complicates things a little bit, and we need to then calculate the amount of BOD we added with our dilution to account for the total BOD and ultimately solve for the BOD of the wastewater, which is what we're interested in. Okay, so I'm going to do a quick drawing. So if we have a total volume of 300 milliliters, and then we add in a bunch of dilution water, so I'll call that VD for dilution, and then we have some wastewater at the bottom. I'm just drawing it as like top, middle, bottom, just as if you added one and then the next, and that makes a total. They're going to mix, right? It's not actually layers like that. But just as a visualization, we have a little bit of wastewater, a lot of dilution water, and that makes some total. Well, that's how we ought to be thinking about it in terms of finding the BOD in the wastewater. That's going to be relevant to the amount of volume of that wastewater we put in there, right? So our mass balance is essentially going to be for the mixture, BOD5M for mixture, times the volume of the mixture is equal to the BOD that was added in the wastewater times that volume of wastewater we had. So it's just a very generic mass balance, right? It's V times C. The volume times the concentration, plus the amount in the dilution times the volume of dilution. Okay, so that gives us a framework to solve for the amount of BOD in our wastewater. We just have to know something about the BOD in the dilution water. And typically, operators will do two simultaneous experiments. They'll just have a bottle with just the dilution water with the bacteria seeded in it, just to see how much BOD that contributes. And they don't really need to dilute that. It's already diluted. So you just put that aside, measure that, and do your actual wastewater, diluted wastewater, and you'll find this value and you'll find this value as experiments. So it'll be like, this will be derived experimentally, this will be derived experimentally, and this then is calculated. Okay, so you get observations for the mixture, you get observations for just the dilution, and you use that to find the BOD of the wastewater, which is what you're after. Okay, we could rearrange this equation to get an equation just as BOD of the wastewater, and it's convenient to do so with values of just those experiments and that dilution factor P. I'm going to skip today the derivation here. It's just essentially deriving from what we just looked at. The BOD of the mixture times the volume of the mixture is the BOD of the wastewater times that volume, and the dilution of that volume. So that's where we start, and then we just do a few clever tricks with P. We can define P. We know P is here, but you can also say 1 minus P is equivalent to this. It's just a little bit of algebra. I'm going to skip over it right now. It's not that important anyway. Just letting you know that this equation does get us here. Okay, so it's a derivation, and this is a handy equation then that we can use to calculate BOD in our wastewater directly if we know the BOD of the mixture and if we know the BOD of our dilution water, and then of course that dilution factor that we use to dilute the wastewater. Okay, and you will have this equation on your exam. I'll probably won't get to posting that. I might be able to do that today. If not, it'll be after the break. Okay, so that's all I really wanted to cover today. We'll go, I'll post these slides. We'll cover the rest of the slides next time. With that, have a happy Thanksgiving.